So if your derivative involves an x and a y, that means that the function that it came from is probably a little bit more complicated. And we saw that with our slope fields, that if it had an x and a y, it ended up looking like a function that was not a straightforward polynomial type of function. So if we're solving something like this, the first thing that we want to do is if they have y prime, we want to go ahead and change that to dy dx. This is really just a notation thing, but I think it's going to help us make more sense of why we're going to put things where we do. So the goal of this, I do want to take the integral at some point, but I want to go ahead and move variables around to where they make sense to take the integral. So I'm going to divide both sides by y so that my y is on the left side. So if I divided, I'm going to have 1 over y. At the same time, I'm going to go ahead and multiply my dx to the other side, so that on the left side, I've got 1 over y with respect to y, so taking the derivative with respect to y, our radical x with respect to x. This way, when I take that next step of solving a differential equation where I integrate, it's not really a big deal to take the integral of this with respect to y or the integral of this with respect to x. So this is called separation of variables, and really it just means that I want anything with a y on one side, anything with an x on the other side. So now my integral of 1 over y, I'm going to have to remember things from chapter 5, is the natural log of the absolute value of y, which equals my integral of the radical of x with respect to x. So I've got raising my 1/2 by 1, I've got 3 over 2 divided by 3 over 2, and then my plus c. Now technically when I take the integral of the left side, I have a plus c as well, but remember that it's just a number, so if I were to subtract that c to the other side, now I've got a new mystery c, so it really doesn't matter that there's 1 on both sides, we're just going to keep 1 with the x's. Okay, so now our goal is to clean this up and to solve for y somehow. So I can clean up my fraction, but I'm also going to need to do some finagling to get that y by itself. And remember that in logarithmic equations, anytime I'm wanting to get that argument by itself, I can go ahead and rewrite it as an exponential. So I've got my base e to this very large power, so I've got e to the 2/3 x to the 3/2 plus c equals y. And then typically to make this a more normal form of this, we would go ahead and think through the fact that if I'm raising e to this power plus this power, that's really the same as saying e to the 2/3 x 3/2 times e to the c. And then we would just say that this e to the c is actually just a new constant, and we would go ahead and redefine this as a new variable c. So in the end, we would say that y equals this c to the e, or times e to the 2/3 x to the 3/2. And that is our general solution. So it ends up that instead of adding the c out to the side, it's actually going to end up being, if you remember from exponential equations, that this is the initial value. So if we were talking about exponential growth, then this would be that value that it started at. So oftentimes these types of problems are put into word problems. So we're going to look at, this is number 22 in your textbook of section 6.2. It tells us that the rate of change of n is proportional to n. Okay, so first of all, if we're talking about the rate of change of n, they're saying n prime. And if it's proportional to it, that means directly proportional. So I've got some k value times n. So this would be our rate of change of n is proportional to n. So then it gives us several scenarios when t is 0, when t is 1. It wants to know what n is when t is 4. We're not going to worry about that just yet. That is all that specific solution of actually solving for c to see what that function looks like. So the rest of this, we're going to ignore that for a second. Let's go ahead and integrate. We're going to do what we did on the other one. Since we're talking about with respect to time, that is important because that's going to make this a dn dt. So that means when I separate my variables here and I'm moving my dt to the other side, I really want to only keep things on the right side that have t in them. And since I don't have anything with t in it, I can leave the k over there. It's a constant, so it really doesn't matter. But I do want to move the n to the left side. So dividing both sides by n, I'm going to get a 1 over n dn. On the right side, a k dt. So now I'm ready to integrate. My integral of 1 over n is going to be that natural log of absolute value of n. And then on the right side, since I'm integrating with respect to t, I will have a kt plus c. Remember, k is a constant. So I'm going to have, if it was a 5, I would have 5t or 5x. So I've got a kt plus c. Just like on the last one, if I'm trying to get n by itself, which is what I'm trying to do, I'll have my base to the power of kt plus c equal to n. To put it in that form where c is my initial value, I'll go ahead and say that this is e to the kt plus e to the c. So I'm going to make that a new c value, and I'm going to go ahead and write it so that you can see what's happening here. But we're making this whole value into a new c. And here is our general solution for the exponential equation. And really it's going to look very similar to that every time for exponentials. But now I'm ready for that specific solution. So number 22 is asking me when t is 0, n is 250. So if I imagine t being 0, that is really the initial value because, well, t is 0, but also because if I raise e to the 0 power, I'm going to get 1. So whatever n is going to end up being whatever c is. So that first piece of it is just telling me that that nc is going to end up being 250. So now I have a new equation that n equals 250 e to the kt. So now they give me another situation that when t is 1, n is 400. So this is one that I do want to go ahead and plug in. So we've got t being 1, so this is just going to be a k. And I want to figure out what that k value is. We did this in pre-calc, where I'm dividing both sides by 250. And then in order to get that k by itself, remember if I'm stuck in an exponential or stuck in a log, I want to change the form. So if I change the form of this, I'm going to have a log base e, or a natural log, of 1.6 equals k. And you can either leave that as natural log of 1.6 for k, or you can go ahead and get the decimal approximation. Just make sure that you go several decimal places. But now that we know the value of k, I have an even more refined equation. Got 250 e to the natural log of 1.6 t. So now I have the full equation for n, and then the last step for this problem was to find the value of n when t equals 4. So now I can plug in my t equal to 4. And let's see what we get. So we get that n equals 1638.4 at that time of t equals 4. They didn't give us any context for this problem, but say we were talking about the growth of bacteria. That would mean that there were 250 bacteria present initially. This natural log of 1.6 is telling us that it is growing because that's a positive number. It's greater than 1. And it's growing at that rate. And then our 1638.4 is telling us that that's how many bacteria would be present at t equals 4. Again, just making up some context there, but that's what it would mean. So the last thing that I want to talk about today is Newton's law of cooling, which uses what we've been talking about. Newton's law of cooling says that the rate of change in the temperature of an object is always going to be directly proportional to the difference between the object's temperature and the temperature of its surroundings. So in layman's terms, if you have a hot potato and it's in a cold room, then that rate of change of the potato is going to be greater than if that hot potato is in a hot room, because it is closer to the temperature of its surroundings. So if we're writing a differential equation for this, and it lets us know that T is the object's temperature, T sub 1 is the temperature of the surrounding medium, and lowercase t is time. So a lot of T's in this to be spelt. So our differential equation, since we're talking about the rate of change of temperature, we're going to call that the dt. So the change in temperature with respect to time, the object's temperature with respect to time, is going to be directly proportional to the difference between the object's temperature and the temperature of the surrounding medium. So since it's directly proportional, we'll have that K, but then the difference between the object's temperature and the surrounding temperature. So there's our differential equation. To find the general solution, we're going to do what we have been doing and move my T minus T sub 1 to the left side. My K can stay. My dt with respect to time is going to move to the right, and then I can go ahead and integrate. So I integrate the left side, I'll get the natural log of the absolute value of T minus T sub 1. And then on the right, my kt plus c. Solving for trying to get the object's temperature by itself, I'll have my base e to the kt plus c equals T minus T sub 1. And then I want to go ahead and add my T sub 1 to the other side. I want to go ahead and make this look like one of those general solutions, where since I have times e to the c, I'm going to bring the c out front. So this is going to look like that's T sub 1. So that is my general solution. So now we're going to look at our specific situation, solve for a specific value. It tells us that we've got some object removed from a furnace. So you can be creative there, whatever object you want to remove from a furnace. It's placed in an environment with a constant temperature of 90, and its core temperature is 1500 degrees Fahrenheit. So it's telling us a lot of information here. First of all, if the environment is always constantly 90, then I am allowed to say that that is T sub 1 in my equation. If it's never going to change, then I'm allowed to just say that that is 90. My 1500 definitely is my initial temperature, because that's what it is when I take it out of the furnace. But we do have to be a little careful here, because if I plug in 0 for my T being time, I'm not actually going to end up with C being 1500. So I need to explore this a little more. So if I know that my temperature is 1500, when T is 0, I can go and plug in all of those things. So my T sub 1, remember, is 90. So it's going to be really close to 1500, but not quite, because I've got my e to the 0 is 1. So I have the c, but I still have the plus 90. So it's actually going to be 1500 minus 90. So my c will end up being 1410. So now that we have our T sub 1 and our C value, we're ready to look at the next situation and to solve for K. So now we're using the fact that 1 hour after it's removed, the core temperature is this 1120. So plugging in 1120 for our T, and then, or sorry, for the uppercase T, and then 1 for time. See if you can go ahead and solve for K. So after getting that e to the k by itself and then rewriting it in logarithmic form, we should get that k is the natural log of 0.73. Or if you did go ahead and figure out what that was, it's about negative 0.313. So that at least tells us that this is decaying, which we know should be true, because the temperature of this object should be going down. So if you wanted to see if that was negative or positive, that might be helpful. So now that we have K, we're ready for that last question that wants to know, find the core temperature 5 hours after the object is removed from the furnace. So this will be kind of interesting because we had something that was very hot, 1500 degrees in a 90-degree room, and seeing what's going to happen after 5 hours. So we're just plugging in 5, see what you get. So after 5 hours, it looks like the temperature of our object is about 382.303 degrees Fahrenheit. So drastically different than when we took it out of the furnace. Still too hot to touch. So you can't just focus on the one toy, because really your main focus is that you want to be where the people are. So you don't have actual legs. You've got a tail, and you want legs. You want to be where the people are. You're just fixed on this one toy.